Greetings everyone. Welcome to my YouTube channel for Kangaroomaths&Science Academy. Ladies and gentlemen, today I want to take you through data science project, which is for part 2 for market capitalization using McDonald's data set. Ladies and gentlemen, in the first video, we went through data analysis using McDonald's data set, particularly in looking on the factors that are actually affecting the market capitalization. All right, in the project, ladies and gentlemen, the first part of the project, which I will share a video below, I went through what is called the EDA, which is the Exploratory Data Analysis, where I was actually looking on the factors that are affecting something called market capitalization. And in the first video, ladies and gentlemen, we went through the statistical analysis. We went through what is called the ADA, where we wanted to uncover the factors that are actually affecting the market capitalization. However, in this video, ladies and gentlemen, which is for part 2, we're still using McDonald's data set, but this time around, we want to come up with a way in predicting those market capitalization. So we want to come up with market capitalization predictions, and also coming up with something called model deployment, where we'll be using functions that are under Streamlit. So we'll be using Streamlit to actually deal with model deployment in order to predict market capitalization. Then, without wasting time, ladies and gentlemen, let's now start. However, in the first video, we went through problem statement. We explained the key determinant. We explained what is market capitalization and how can one calculate market capitalization, and what are the other factors that can affect market capitalization. We went through that. And now we can move on to the objective. Under the objective in the first part, the objective of the first video was to uncover the major determinants of market capitalization using what is called the EDA. Also, when we're given the financial ratios from McDonald's data set. But in this video, we want to come up with a way of predicting this market capitalization and also performing something called model deployment. In other words, creating an app, and in this app, we're able to, given certain futures, we can able to predict the market capitalization. This is what we'll be doing now. Right, again, we went through the data descriptions. I think I'm not gonna explain this. I've explained this in the first video. Then now we'll import the necessary libraries. However, in the first video, ladies and gentlemen, the libraries that we're using was Pandas, NumPy, Matplotlib, and also the Seaborn. Now I've added other libraries that will actually enable us to deal with model building. All right, we went through like number 1 from the sklearn. We're going to import something called the mean square error and the mean absolute error, and also the R-squared score. These are actually performance measures. These are performance measures for regression model, ladies and gentlemen. So we are going to import this, and again we are going to split the data into train and test. And we are also going to use something called cross-validation. And also we are going to we'll be standardizing our data using something called standard scaler. And also, and also we'll be talking about the issue of like regression model, the other boosting, gradient boosting, random forest, bagging, and also something called k-neighbors model, and also the support vector regression model. And the other one is called the XG boost regress, which is called the extreme gradient boost. So these are examples of the ensemble models, particularly when you talk about the other boosting, the gradient boost, the random forest, and the bagging. Then again, this is the libraries that we're going to import. And also we are going to suppress the scientific notation of most of the data frame. We wanted them to be rounded to 3 decimal places. Most of the data frame that we'll be using, actually we set them to round its values to 3 decimal places. And also this function is to define the maximum and the maximum number of columns that we actually need to display, which is actually a good practice when dealing with data analysis. And also to suppress the warnings. This one went through this in the first video. So let's now run the libraries. While running the libraries, actually here, we are going to import to read the McDonald data set using the pandas. Actually, I went through this in the first video. So I'm not gonna waste time here, ladies and gentlemen, because the objective of this project is actually to deal with model building and coming up with model predictions, also doing model deployment. So we'll just wait for the libraries, like for the program to run all the libraries. Then from there, we'll read the data set using pandas. It's just taking some time, just a minute. Then after reading, I think we'll display the first 5 rows, which we've done in the first video. The last 5 rows listing all the futures. So I'm not going to spend a lot of time here. Right. Without wasting time, okay, still reading the modules, still importing all the necessary libraries. And particularly here, the focus is to actually build these regression models. Why is it called the regression models? Because we are dealing with a supervised learning techniques. And a supervised learning techniques is the one that has the input data and also have the target variable. So which you call it the labeled values. It has labeled data. So in that regard, since you have the input and we also have the output, which is the target variable, this is an example of a supervised learning. And this supervised learning has to do with, it is a regression type of the supervised learning. So hence we are going to use linear regression, the other boosting, the gradient boost, the random forest, and the bagging regressor, and also the XG boost and the support vector regression. So these are the models that we are going to focus on. Let's check if it has run. And now, so that we can be able to continue. Still loading. Now it's done. Let's now read the data. Now we'll be reading the data. Let's display the first 5 rows. We've done this in the first video. I'm not going to spend a lot of time here. The last 5 rows list the data columns, and also here we have to sort values by using yes. We went through this in the first video. Went through this in the first video, so I'm not going to spend a lot of time here. Reset the index. Also, let's check the data types. Then now again, let's display the statistical summary of the data set. We went through this in the first video. For example, if you look at the earning, the mean for the earning, it's roughly 6.22, whereas the median is 6.86. So you can easily see that the mean is actually less than the median. So we know that when the mean is less than the median, it means this data is skewed to the left. It is skewed to the left, or it is negatively skewed. So I went through this in the first video. Now let us now move on, ladies and gentlemen. Now let's check if you can see that there are no any missing values here. Let's check for any duplicates. They're not there. Let's now create a copy of the original data set. I think we went through this in the first video. Now here we perform the EDA, Exploratory Data Analysis. I'm not going to explain anything here because we went through this in the first video. Ladies and gentlemen, we went through this in the first video. So you can easily see that the market capitalization is skewed to the right. Here is a box plot for histogram. The box plot and the histogram for revenue. The revenue, it's approximately symmetrical, but you can easily see that it's slightly skewed to the left. And also, let's look at the distribution for the earning. Went through this in the first video. You can see that the distribution of the earning skewed to the left, as I said earlier, because this is the quartile 1, this is the quartile 2, this is the quartile 3. So you can easily see that more space is actually on the left of the median. So which means this is skewed to the left. So that is the distribution for the earnings. Now we look at the display. We display the box plot and the histogram for price to earning. We went through this, ladies and gentlemen. Here we're just creating a list to actually display the remaining box and histogram columns. Then now from here we'll have to display the line plot. After displaying the line plot of each, we'll look at the bivariate data analysis. Actually, we'll look at the scatter plot here. I think I went through this in the first video. If this is your first time, ladies and gentlemen, kindly visit my first video so that you can be able to understand what I'm actually doing here. Because the focus for now is actually on model building in order to predict market capitalization. Let's check here. It's still displaying the information here. This is the data for price to sales, price to book value, operating margins, the distribution, earning per shares. So you can easily see that the earning per share is skewed to the left. And the last one is the share outstanding. So this is actually the distributions for the data. Now, let's now continue with displaying the line plot. I went through this in the first video, ladies and gentlemen. I'm not going to spend a lot of time here. So this is the line plot for the market capitalization per year. So here I actually displaying all other futures, looking at the trend of each futures per year. We explained this in the first video. There is a link below. Kindly follow the link and don't forget to like, subscribe, and hit the bell button. We're still reading. This is still under the exploratory data analysis, ladies and gentlemen. Okay, it's completed. Let's now move on to the bivariate data analysis. This is the function to display the scatter plot. Let's display the scatter plot for market capitalization and revenue. Actually looking at the trend, whether there is a strong correlation or not. I went through this in the first video. So this is the market capitalization, scatter plot and revenue, market cap and earnings. And you can easily see that between market capitalization and earning, there is actually a positive correlation between market cap and the earning. But however, this correlation is not that very strong. The correlation is not strong. So we'll look at the correlation matrix, or it's still reading. Market capitalization and earning per share, number of shares outstanding, market capitalization and the cash on hand, dividend yield, is the dividend split adjusted in dollars, and also the net asset, total asset, total liabilities. Okay, then it is done. Let's now calculate the correlation matrix. This is also under the EDA, right? We went through the correlation matrix. We displayed the heat map in order to look at the correlation between the target variable and the independent variable. So you can easily see that between the market cap, like what I said earlier, between the correlation between market capitalization and for example, and price to earning, there's price to earning, it's roughly 0.64. But the correlation between market capitalization and price to book value is 0.97. You see that there is a very strong positive correlation between market capitalization and some of the variable, but particularly the price per book value, and the other one, the price per sale, and the other one, it is the earning per share. The other one, it is the let me check this. It is the operating margin, but with the operating margin has, let me check something here. Is it operating margin or no, it's not the operating margin. It is the shares outstanding. Shares outstanding, there's a very strong negative correlation between the market capitalization and the shares outstanding. However, in other some of the independent variables, they're also highly correlated by themselves. For example, if you look at the dividend stock and the dividend yield, the dividend stock and not necessarily the dividend yield. Okay, the dividend stock and what is this? The price per sale. There is a correlation of 0.93, which is it's a higher correlation. And this might lead to something called multi-collinearity issues. Which becomes a problem actually when we are going to deal with the interpretations of the coefficients of the models. This is actually a problem. So we need to correct this multi-collinearity issue, which actually occurs when the independent variable are highly correlated to each other. So you can easily see that this is the correlation matrix for the numerical columns. So in terms of the observation, this is what I have extracted in the data set. There is a strong positive correlation, particularly with the ones that have a correlation that is bigger than 0.8. It exists between market cap and revenue, market cap and earning, price to earning and price to sale. And it's particularly when we talk about price to earning and price to sale, these are actually the independent variable. And since the highly correlated means one of these should be dropped in a data set because they're highly correlated. Operating margins and earning per share, these are highly correlated because usually when like to calculate the operating margin, they actually use what is called the earnings. It's earnings divided by the sales or the revenues. Whereas earning per share, it's also the earning. They take the earnings, then they divide by the number of shares outstanding. So you can easily see that these are actually factors. Yes, they have to be highly correlated because of this factor of earning, because of actually the earning. Then now the dividend yield and the dividend amount, and also there's a negative correlation between market cap and the shares outstanding and the cash on hand, and also the net asset and the total liabilities. So it means things like this, share outstanding and cash on hand, we need to make sure that we correct this multi-collinearity issue. Also on the issue of the net assets and the total liabilities. And some of this, for example, when you're calculating the net asset, remember the net asset, it's like we're taking all the total asset, we subtract all the total liabilities. So you can easily see that when we are determining the net asset, we use total asset together with the total liabilities, which means we need to drop one of these factor to avoid something called double counting, and this might lead to something called data leakage. So now in this, we can now move on to the next slide. However, ladies and gentlemen, correlation does not imply causation. I think I've explained that in the first video. There's a moderate positive correlation with correlation that is between 0.5 to 0.79 between revenue and earnings and price to earnings, operating margins and earning per shares, and also moderate negative correlation between price to earning and price to book value. So, but now in terms of this, we can conclude that a higher correlation actually suggests that the matrices they're actually moving together, whereas a very low correlation indicates that there is a less relation between the two variables. But a strong positive correlation between the market cap and other metrics. This is reflect the size effect, particularly in finance. Negative correlation between the shares outstanding and the cash on hands or the net asset may indicate that the company with more shares outstanding will tend to have less cash or assets in terms of its position. So this is what I actually extracted from this. However, we can now move on to something called future engineering. in the future engineering, first of all, we'll have to drop the year column because it is an unnecessary column. It will not help us in predicting the market capitalization. Let's now drop the year column. Now we want to check the presence of multi-collinearity, like what I said now, that multi-collinearity actually occurs when the variables or when the independent variable are highly correlated. And this might have a negative impact in model building. So to do that, you are going to like, there's a code which we'll use to actually select those highly correlated matrix, where we define the correlation with the specific inputs, looking at the cutoff, the threshold of what percentage of this correlation are actually looking at. So now first we'll just create a set, then now we'll calculate the correlation matrix of our numerical data set. Then now we'll create an absolute value to actually sort all the values, all the correlations that have the value that is bigger than a specific cutoff. Then after that, it has to display them, and it has to add them or append them into the set in order to display those features. So in so doing, ladies and gentlemen, we'll now run this definition. Let's now run the definition. After running the definition, we'll just select the numerical columns in the data set. This is just a function to select the numerical columns. So just run this. And again, let's now display the highly correlated columns with the correlation that is above 0.8. So it means here we are, like I've set a threshold to say any matrix that has a correlation that is bigger than 0.80, it's regarded as highly correlated features. So this is my threshold. So you can, someone might use 0.70, but for on my side, I've used 0.80, which means any features that I have a correlation that is bigger than 0.80 are highly correlated. So what we're gonna do here is we'll have to call that function. We'll have to call this function. This is the function that we actually called. Then now this is the data where we only select the from the data frame, we only select the numerical columns only, but with the interest of the cutoff to be 0.80. Then now, we'll display this to show all the features that are highly correlated. So the features that are highly correlated, we have operating margin, price to sale ratios, net assets, total assets, share outstanding, earning per shares, total assets, and the other, which means because of these features, since they're highly correlated, means we need to drop some of these because they will not, they will affect the models in terms of its model, in terms of interpreting the coefficient due to something called multi-collinearity issue. Now, without wasting time, before we drop all the columns, we need to first understand that. Let's now just try to observe or try to compare all these features together with the target variable, because yes, you might find that operating margins and price per sale are highly correlated, but however, operating margin and the market cap, it's highly correlated as compared to the price to sale. What does this mean? It means that in predicting the market capitalization, operating margin will be a good future to predict the market capitalization as compared to price to sale. I'm just giving an example. So which means now we are going to observe, we're going to look at the correlation between these highly correlated futures and the target variable. So what I'm going to do here, I'm going to create a list of those correlated futures. So this is just the code that I've used to create a list. Then however here I want to calculate the correlation between the target variable, which is the market capitalization. So I wanted to look at the correlation between our target variable, which is the market cap, together with those highly correlated futures, which means here we want to look at the correlation between market cap and operating margin, market cap and price to sale, and the others. So that we can be able to know which one between these can we drop if it does no impact towards the target variable. So here what I've done is that I've just created an empty list and also define a correlation function where it, as an input, we're gonna put those futures, those listed futures. So I'm gonna say for any item that is inside these futures, what I wanted to do, I wanted to calculate the correlation between that item and the market cap. And after calculating the correlation, I wanted to append or to append this value inside the empty list. And at the end, it display that list. So this is what we are actually looking for. So now let's run this. Let's run this function. Then now let's this is just the list of those correlated futures. I've just created a list of those correlated futures. Then now I'm gonna calculate the values. I'm gonna call this function to say the correlated function which require the futures, which is the correlated futures, which I've included there. Now you have to calculate the now here we are just creating the data frame. We're just creating the data frame of the values of the correlated the values that we have calculated here. Then again, we need to rename the columns in that data frame, like the columns where it has a data frame of 0 to be a market cap. For example, if I run these two only, let's run these two only. I just want to show you something. Let's run this. So when let's display the data frame dot head. You can easily see that it's just showing earning per share, net asset, but here we need to change this column so that this becomes the market cap. We want to change that index to become the market cap. So in doing that, let's run the whole code. Still taking some time. So while still reading, since we want to compare, we want to display the correlation between our target variable, which is actually called the one. Okay. It's because I said the head. Okay. Let's display this. All of them. Data. Okay, press through. Okay. Just change something here. Fine. Now let's display this. Okay, let me describe this. It's okay. Let's now show that as transpose. Let's display the correlation data frame transpose. So here, actually, I wanted to explain, if you look at this, here is just the correlation between market cap and earning per share, 0.956. Between market cap and net asset, it's negative 0.80. You see that there's a negative correlation between market capitalization and net asset. But between operating margins, they were 0.877. The correlation between market cap and share outstanding is negative 0.93. Dividend stock split in US dollar is 0.97. Dividend yield is 0.09. You see that there is a very low correlation between market cap and dividend yield. And the other one is the price to sales, and which is 0.97. The other one is the total liabilities, total assets, and total debt. But looking at this, we can easily see that we know that a very high positive correlation in case that there's a very strong relation between the futures and the target variable. But now there are those correlations which are actually close to 1 or -1. When the correlation is very high, such that it is very close to 1 or -1, it suggests that the futures actually might be overly or similar to the target variable. And when a future is actually similar to the target variable, it does not make any impact towards predicting the target variable, because its correlation, it's close to 1, which means there is actually, it's like, for example, if you want to look at the correlation between market capitalization and market capital, it's 1. So which means a very high correlation that is actually close to 1 or -1, which means that these futures and the target variable are actually similar. Now, again, if there is a negative correlation, it indicates that there is an inverse relationship, which could be useful in terms of modeling. But based on this, if you look at the earning per share, the earning per share has a correlation that is actually closer to 1. The earning per share correlation between market cap and earning per share, it's a value that is actually closer to 1, 0.96. For example, even the stock dividend split has a correlation that is actually closer to 1. Even the price to sale has a correlation that is actually closer to 1. Even the total liabilities, total assets, and also the total debt. But in terms of my analysis, yeah, I've realized that since the earning per share and the target variable has a correlation of roughly 0.96. So this is an example of a perfectly correlated situation between the earning per share and the market cap, which means we can say these are actually roughly similar, which means the impact of earning per share would not necessarily affect the market cap, which means this is one of the variable which we can actually drop. We can actually drop because there is a perfect correlation. Also, looking at the issue of dividend split, there is a perfect correlation of 0.97. And also the price to sales also, this is the highly correlated. And this might lead to something called multi-collinearity. So it means we need to drop the earning per share, and also we need to drop the dividend stock split, and also we need to drop the price to sales, because they have a perfect correlation with the market cap. Their correlations are very higher. Then now again, one other thing is we need to look at this. We know that when we are calculating the net asset, as I said, net asset is actually calculated by using the total assets where we subtract the liabilities. So it means the net asset is calculated by taking the total asset minus total liabilities. So which means that if we are taking the net asset, we need to drop these two to avoid the double counting. So in this, and one other thing, the net asset is more closely related to the shareholders' equity, because this has to talk about the net worth. And remember, in a company, investors are actually interested on the net equity or the net asset after the company has subtracted all the liabilities. So which means net asset must not be dropped. So it means here we can keep the net asset, operating profit, share outstanding. We drop the dividend, stock split, earning per share, price to sales, and the other one is the we'll leave the dividend yield. Total liabilities and total asset will drop them, because why? Already if we are taking the net asset is calculated by subtracting net asset minus total liability. So to avoid double counting, we need to drop the total asset and total liabilities, like what I have said there. So in terms of the analysis, ladies and gentlemen, so this is what I will do here. So we'll only drop the highly correlated, the one that has a higher correlation with the target variable, which are perfectly correlated with the target variable, and also will drop the total assets and total liabilities. So this is a function that I've created to drop the earning per share, dividends, stock split, price to sales, total liabilities, and total asset, to avoid dropping all of them. So let's now drop this. In dropping this, now let's now perform data processing. Actually, since our data set has no missing values, so it means now we'll just split the data. Let's now split the data. In splitting the data, we'll just create we'll first drop the target variable, and again we'll select the target variable. So this is the function. Then secondly, we'll now split the data into training and testing using 70:30. So it means in terms of the analysis, we want the training data, we want 70% of the data. We want 70% of the data to be training, and also we want 30% to be testing data set. So this is what I have actually created here. Then now, let's now run the function. Let's run the function for splitting the data. Let's check the shape of the data. The training set has 14 rows and 10 columns, whereas the testing has 7 rows and 10 columns. Let's confirm the percentage. So if I say 10 divided by 7 plus 14 in total, and we multiply that by 100, you see this only, it says 0.33, which is roughly 30% of the data. Then now, if we say 14 divided by, so you see it says roughly 70%. Yeah, it's roughly 67%, but generally it has to be 70%. Right, then now from here, let's check the info of the data set. Already we know that our data set, it's just consisting of the floating numbers. The numbers are in decimal form. Let's now display the first 5 rows of the X training. First 5 rows. Training set. Then now, yeah, let's reset the index, because you can easily see that the index are not reset. Now, after resetting the index, let's now select the first row of the column, because I want to use this for model deployment. So in terms of this, we can see that the revenue is 15.4 in billion, earnings is 1.6, because I want to use this for model deployment. Then now let's now standardize the data set using standard scalar. Then now I'll create a data frame for the scaled data set. Now I'm gonna perform the mesh, the regression models. But first of all, we want to talk about what is called the mean absolute error, which is actually is the average absolute difference between the predicted and the actual values. And the lower the value, the better the model. And also we have something called the mean square error, which is actually the average sum of the squared deviation between the predicted and the actual value. The lower the mean square error, the better. And also we have something called the root mean square error, which is the square root of the mean square error. These are performance measured for regression, ladies and gentlemen. So, for example, if we talk about the mean square error, this is the sum of the deviation from the true value and the predicted value squared divided by the n, divided by the number of observation. But if we put the square root inside this, then this becomes the root mean square error. Actually, the mean square error is there to minimize the residual, to minimize the residuals, or something called the errors. We want to minimize the errors by using something called the mean square error. The lower the better, the lower the better. But now in terms of the mean square error, when we are using the root mean square error, it is easier to interpret the root mean square error as compared to the mean square error. And the lower the root mean square error, the better. And the other one is called the R squared, square, which is actually the measure of proportion of variance in the dependent variable, which is explained by the model. And these R squared is calculated by taking 1 minus the sum of the square errors. The sum of the square of the regression divided by the sum of the square of the total actually in the model. So this is the formula for calculating the R squared. And this R squared error, it's actually ranging between 0 and 1. So it means the R squared error, it's ranging between 0 and 1. And again, which means that 1, it indicates that there is a perfect fit. There is a perfect fit in terms of model building. In overall, we can say it indicates the overall goodness of the fit of the model. And the higher the R square, the better the model, so that we can use it for prediction. So the higher the better, the higher the better the model it is. However, in terms of the root mean square errors, the smaller the root mean squared error, the better the model. These are regression models. So what I'm going to do here, ladies and gentlemen, I'll just create a function, we'll define a function which will actually perform will calculate the performance measures, particularly the mean square error, the root mean square error, the mean square absolute error, by using something called the sklearn library. So here, first of all, we'll predict the predictors using our input. What is our input in terms of the definition? We have to put the model, the predictors, and the target. What is the target variable? The target variable is that list, that variable that consists of the market capitalization. So this is our target. So within this, we'll use this to actually, number one, we'll use the model. We will use the model to predict using our predictors, and also we'll calculate the mean square error by using mean squared error function, which is from scikit-learn. Then now looking at the target, which is the real value, and the predicted. And again, we're going to calculate the root mean square error, which is the square root of the mean squared error. So that's why here I said the square root of the mean squared error, and also going to calculate the mean absolute error. In terms of the mean absolute error, is that in mean absolute error is just the sum of the absolute. We use absolute value from the real and the predicted value divided by n. This is the function for the mean absolute error. Then again, we went through the R squared score, where it actually as input needs the target values and the predicted. Then now we're going to create a data frame, but using a dictionary to say with the root mean square error as our key, then our value will be the root mean square error. Then the mean square error as our key, then the value will be mean square error, just like that. Then now we'll return this. So what I'm going to do, ladies and gentlemen, I will run the program. Let's run this. Let's run the definition. So here I was just explaining the definition. So let's run this. Now, in terms of our score, I will use the mean squared error to compare using cross validation. So now here what I've done, I've created a list of the model linear regression, k-neighbor, random forest, Bayesian, gradient boosting, other boosts, support vector matching, and the gradient boost. Then I'll say for the name and each model in this model. Remember, this is the name and this is the model. Then now I want us to calculate the cross value score, looking at the model and taking into account our X train and our Y train and our scorer. But for a cross validation, we set it to be 5. Let's now run this in order to compare the model performance, ladies and gentlemen. So you can see that under linear regression, when we're using cross validation, it has the mean square error of 980. K-neighbor has a mean square error of 830, which is less than that of the linear regression. Then the random forest, its mean squared error, it's 418.86, which is less than that of the K-neighbor. Bayesian, it's 420. Gradient boost has a mean square error of 225. You see that when comparing this, you can see that gradient boosting in terms of the mean square error, its mean square error, it's actually smaller than the other, which means in terms of cross validation, it is the one that performs better than the other when looking at this, because it has the smallest mean squared error. And if its mean squared error is 235.87, what could be the root mean squared error of that? So we can compute, so we can say NP dot square root. We want to compute the mean squared, the root mean squared error of that. So it's 235.8709. We want to come to look at the root mean squared error, which is the square root of this, which will be a smaller value. So you can easily see that it means that here, while we are still waiting for the XG boost, the gradient boosting is the one that is the smallest in terms of the mean squared error. Remember, we said the lower, the better the model it is. The lower, the better the model to be used for prediction. But however, we need to actually, this was just the cross validation. We actually want to perform the analysis using the trained data and the testing data so that we can compare the performance to check whether we're having an overfitting or an underfitting issues in order to compare the model performance so that we can, it's either we perform hyper parametric tuning or we just continue with model prediction. So we're just waiting for the XG boosting. The XG boosting. But look here, if you look at the support vector machine has the mean square error of 2,668.70. You see that this mean square error is actually the highest. So which means support vector, it's not a good model to use for prediction. It's not performing good as compared to other model. And the second best performing model in terms of cross validation here, I think we can look at the random forest. Random forest also, it's also performing better as compared to other. And the third one is the yes, it's random forest, and also we have the begging. Begging also performs better with a mean square error of 420 as compared to these other ones. So while we are waiting for the model to complete, let's just wait for the model to actually run. Then boosting. Okay, while we are waiting, say, yeah, I will just check the performance for each model using the model that I've defined earlier. This one where I said the model definite performance regression. So it needs the model, it needs the predictors, and it also needs the target. So what I'll do is I'll call that function one by one. So what we'll do, I'll say model performance, and I'll first call our model. Here it's our model. Then after the model, I will have to feed this model. This is actually the models, because I'm actually calling the function, the model, then feed this model using the X train. Then this will be my predictor variable, and this one will be the target. So it means this part here up until here, this is my model. So I'll just calling the model. So I'll do so for all this, for the K neighbors, for random forest, begging, gradient boost, other boost, and the XG. But for training, Then again, after this, we'll have to look on the performance for testing, using the testing data set. So here I'll just use the testing data set. We actually wanted to look at the performance in terms of the mean square error, the mean absolute error, the R squared. And again, we are going to display this training performance, but using something called concat. So I'm combining all the models. I'm combining all the models, the linear models, the K neighbors. But so I'm combining all the models by columns, and I need to rename all the columns to say in each column, each model must have its own column name. Then from there we'll display that data frame for both training and testing. So it's still reading. Wanted this to display the XG boost results in order to proceed with the next analysis. So, but we cannot proceed if it's not completed there. But you can easily see that a model like gradient boost, this will be, it's a better model to be used for prediction. But however, we will also check in the performance of the training and testing. So we're just waiting for the XG boost result to print in order to proceed. Then from here, okay. It's taking some time. Okay, while we are waiting for this, the strategy that I've used here to drop some of the highly correlated. Since we are dealing with regression, one can also use something called the variance inflection factor method, VIF. One can also use this to drop the highly correlated futures, particularly when we are dealing with a regression in models. Okay, let's check if it's completed. Still running. Okay, it's done now. So now let's just calculate the square root of the. So you can see that the root mean square error for the gradient boosting is 15 point, which is less than the other. So let's now let's check the performance of each model in the training. We want to check the performance of the model in the training. So this is the name of the model. Then this is our predictor. It's completed. Then now let's check the performance in the testing. After doing that, we need to concatenate all the models that are in the training in order to display them as a data frame. And also we need to label them, to label the columns. And after labeling the columns, these linear models, they need to be transposed. So we transpose the result, the performance of the linear model. So what I'm trying to say is that, for example, in terms of the, let's say in terms of the linear regression, we want to see the mean squared error. Is this an example? The root mean square error. We want to see the mean absolute error and also the R squared. So in terms of its results, so in this, so this model and its results, so something like this, then just like that, random forest and the other. So this is what we want to display here, actually. It's taking some time, but it was supposed to have done now because the X-test features are not that much as compared to the X-train. Unless if it's because of this XG boost, you've seen it has taken some time earlier. Okay. Okay, now let's display the training performance for each model. So here's just the function to display the training performance in each model. Creating we're just concatenating. Then same applies here for the testing. Let's now display the results. So you can easily see that in terms of the results for the testing, the linear regression model has the root mean square of 3.43, k-neighbor, random forest, begging, gradient boost. You can see that gradient boost and XG boost and also the linear, but you see that there, the gradient boost and the XG boost, you see that this in terms of the root mean square, these are the best performing models because their root mean square is smaller than the other. But when you look at the mean square error, the mean square error for gradient boosting and XG boost, it's 0. The mean absolute error for gradient boosting and XG boost, they're the ones which are minimum as compared to others. But let's look at the R squared score. Remember we said the higher the R squared, the better. So this one has higher R squared score. Even this one, even the random forest, the begging, and also the gradient boost. It has an R square score of 1, and also the other boost and also the XG boost. So you can easily see that in terms of the R squared score, all these models are actually performing better. But in terms of the root mean squared error, or if we want to compare in terms of the root mean square error, the gradient boosting and the XG boost are the ones which are better, they're performing better as compared to others. Let's now check the result in terms of the testing. In the testing, when we look at the testing, you can easily see that the linear regression in terms of the R squared, it's actually performing good. The k-neighbor, it's not performing good because it has performed better in the training, wherever it is performing poorly in the testing. And this is an example of an overfitting issue. So it means the k-neighbor has an overfitting problem. It has an overfitting problem because it's performing better in the test, in the training, but it's performing poorly in the testing. So it is a problem of overfitting. Random forest, it performed better, but there was a slight drop in terms of the R squared. It has dropped in terms of the R squared, but it shows that it's actually performing good. But the bagging also, it has performed better in the training, and also in the testing has declined slightly so. But however, in terms of the root mean square, the root mean square error has not improved. You see, it has increased from 6.43 and 8 points. So this is not a good model to use for prediction, because it's actually increasing the root mean squared error. But when you look at the gradient boosting, its root mean square error was 0.002. Now it has declined to 0.001. And also in terms of its mean squared error, mean absolute error, and also its performance is performing good. So it means this model does not have any overfitting or any underfitting model, I'm saying issues. Also, as compared to the XG boost. So it means XG boost and the gradient boost, these are the two models which are actually performing better as compared to others. Now, again, when we look at the other boosting and also is performing good. The other boosting is also performing good, because the root mean squared error, it's 1.510, but now it went through the 0.0. So it means this is one of the model that we can use for prediction. So it means in terms of on our analysis, one can actually use gradient boosting, or one can use XG boost or the other boost in terms of model prediction. But I strongly believe that even if we can perform the hyperparametric tuning, the gradient boosting would be a better model to use for prediction. So here it means I'll use gradient boosting as the final model. So I'll use the gradient boosting. I'll use the gradient boosting as my final model to use for prediction. So let me now use the model. So I'm just calling the gradient boosting regressor model, so that I can use that in terms of model prediction. Then here I'll display the important features, like the bar graph to show the important features here. So first of all, this is I'm selecting all the columns that are in the X train. Then now performing calculating the future importance using the gradient boost, and also display them. So let's run this. This will actually show us which are the key factors or the major determinants of market capitalization. So according to the gradient boosting, we can see that the net asset, share outstanding, total debt, revenue, operating profit, dividend yield, and earnings, even price to earning, these are the factors that actually can be, that the major features that can predict or that can affect market capitalization. However, if you look at things like cash on hand and also price to book value, so these are the least factors, the least features that can that have an impact towards market capitalization. So this is our future, the future importance. So let me just reduce the size so that we can easily see it. Let me just make this 12:8. Okay, let me also reduce, let me make it 10:8. The width. Yeah, so I believe you can see the future importance graph. Okay, now let's continue with the model prediction. Right, in this code, I want to predict the market capitalization. The market capitalization using the best model, which is the gradient boost, as I said. Let's now make the prediction. After making the prediction, let's just print the first 5 rows. Let's print the first 5 rows of the data set, just to check, to look at the predicted market cap. So you can easily see that, remember, in terms of the data set, we had standardized this data set using standard scalar. Actually, like to balance the data in terms of predictions. So here, if you look at this, it shows that when the revenue and the earning price to earning price to book value up until the total debt, this is the predicted amount. And also with the second, these are actually the predicted values of this data set according to the gradient boost model. So what we'll do actually here, we'll just do something called model deployment. Actually, first of all, we'll save the model using pickle. So first of all, in terms of the pickle, we'll first import the pickle library. Then we have to create a file, and this file we create it as a write binary mode, and we save it as a file. Then after this, we use pickle to dump this model, which is the gradient boost model, inside this file. So in other words, this will be saved in the Jupyter notebook. We'll have to download this. Already, I have done this already, so let's just run this. So this will be saved in the local Jupyter notebook that I've opened. Then now we'll create an app which will be used to predict the market capitalization. Market capitalization app by using something called Streamlit. Right, in using the Streamlit, this is what I have actually done in terms of the coding. I have imported the necessary library in order to create this market capitalization app. So in terms of this, number one, I have imported the NumPy, the pandas, the pickle, and also the peel for the image, to display the image. And also we need to import this Streamlit as ST. So these are the libraries that we are going to use. Another one that we need to import again is the issue of the standard scalar library, but we can also create a pipeline to incorporate everything here. So in terms of the coding, I've just set the configuration, like how the app should like its page should look like. Now, here is the title page, which is Market Capitalization Prediction App. Then this is just some icons that I've already included here. Then inside this app, I want it to have a banner, and this banner must actually display the McDonald image. Then I will open this using the image library package from Pill. Then now again, I will create a centered title. And within this centered title, you'll see this is the markdown title from Streamlit. These are actually Streamlit functions. So within this is the market capitalization predicting app, which will be at the center. Also, I wanted to display who's the creator of the app, and also what is the email address. So this is what I have actually included in the app. And also inside the app, we also have to include the futures, which will be used to predict the market cap. And these futures is like what we have already seen from the data set. Like if we have the revenue, the earnings, the price per earnings, the price per book value, the operating margins, shares outstanding, cash on hand, dividend yield, net assets, and the total debts. These are actually values. So it means I will just create a Streamlit function. We want it to be on, like, to be a side futures, like we just want to create a sidebar. Within this sidebar, we'll have to create, like, to say this is a number input, so which will just input this, the revenue, will input the earnings, the price to earnings, because are all values. So now, again, from here, we'll define a function. This function will be used to make the prediction. So we'll just call it the model prediction. And this model prediction as an input, it will need the model. It will need the model and also the input users. So the input users is the issue of the revenue, earnings, price to earnings, all the features that are required in order to predict the market cap. Then from there, we'll have to make the prediction to say model.predict using those input users. Then it will have to return this predicted value. Then from there, we need to create a list of those input values. So obvious, the input values will be the one that I just mentioned here. So it will be the revenue, the earnings, price to earnings, up until the total debts. Then again, we'll also have to create a list of the futures, the actual futures that will be needed for the model to actually predict them. So the first one, we have the revenue as the list, earnings. Then again, we have to change the inputs and set them as a data frame. So we're just creating a data frame of these inputs by using input user as pd.dataframe of the input. But we want to set these inputs to be in the form of like the features. We need to index this data frame by using the features. Then after that, we have to load that model that we have saved earlier, the market cap prediction model, as a pickle. But this time around, we want it to open it as a read binary mode. So as a read binary mode. So the RB is just the read binary mode, and it has to save it as file. And also it has to say, to predict like we need to call the model and say model equals to pickle.load. So we want to load that model inside the file. Then now again, we have to make the prediction, and making the prediction. So in other words, we need to call this Streamlit function for a button to say there will be a button that will be provided in the app, and inside this button will have the predict icon, which means within this is the one that will be used to make the prediction. So in other words, we are going to make prediction by calling the function. Remember, the function require the model, and this is our model, by the way, and this is the model that we have actually called. So the model and also the input user, but this time around we want it to be transposed. So then again, in terms of its success, so it means it will just print market cap value in $1 billion, just to be the predicted values, and this should be rounded to 2 decimal places. This is what the app it's actually going to print. So now, in terms of this, ladies and gentlemen, first of all, we need to copy this function, and we have to create a Python file in order to use the Streamlit functions. And to do that, however, on my side, I've already created the Python file. So what you can actually do is just you go to File, then under File, then you open new icon. Then within this, you go through the Python, you click on the Python file, because we want to create a Python file in order to save our model. But already, ladies and gentlemen, I have already created the Python file, but I just want to show you what I'm actually talking about. So it means we need to copy this. We need to copy this code for creating the app. So after copying this, then we'll have to save this inside this Python file. And within this Python file, ladies and gentlemen, we need to download it. So already I've created the Python file in order to use it to make the predictions. So let me just wait for it to open so that I can show you. Because on my side, I've already created the Python file. So you just go to File, then Mode, File, then you go to New, then you go to Python file. And after Python file, then you select this, then you'll have to paste the codes for creating the app. Then this will be pasted under this Python file. You see, it is showing this is a Python file. So this is the one that we need to use in order to create the app. So, but already I have created this py file. So we can just go through it and, okay, let me just waiting for this to open. It's taking some time. Okay, while it's still opening. So in order to call this, we need to run this code here. This is the code that we need to run in order to upload this app code. So to do that, it means we must run this code, which is Streamlit run. Streamlit run. Inside the quotation mark, we need to display that Python file that we have created inside the list. But we are going to do this using the command. This is our command prompt actually. So actually we're supposed to paste the code here, and after pasting the code here, we can rename this. We can rename this as any. We can just say this is, for example, Market Cap prediction app.py file. Then after this, you have to download. I'm not going to do it because already I have created that. Then you come to file and you download this file. You need to download this file and save it inside your local machine. But already I have downloaded the file. This is my Python file that I've already created. So let me just show you. So this is the file that I've already created in my Jupyter notebook. So this is the file, the app that I've created already. So already I've downloaded this, and I also have to download the model file where we saved the gradient boost model together with the gradient boost model. So, but already I have saved this in the local machine. Okay, now let's open the file where I saved the Python files. Right, here is the file where I saved the Python file, which we need to use to display the app, together with the model where we have the gradient boost, which we're supposed to use it inside the app. So this is the file path. First of all, I will copy the file path. So let me just copy this file path because I'll be using it. And then after copying this, I can now go to my Jupyter Anaconda navigator. I'm saying Anaconda navigator. Then within this Anaconda navigator, I'll just open the, remember we're working on the base environment in terms of the project. So what I'll actually do is I'll just open the navigator. Just a minute. I'll just open the navigator in order to run the Streamlit app. Then if you look here, we have the home and there's an environment. So if I can right click here, you see that I have two environments which are on my system. But however, the second one, I just created it. You can also, when you open your Jupyter notebook, it will just show the base root. But in terms, if you want to create another one, which I've already created the one which is called machine learning, but you just come here and right click this icon here for creating the new the new environment. So after that, you see that if I right click here, it will show that I have to create a new environment and to show you the package there. But I'm not going to create them now because I've already created one. Then within this, I want to work under the base root environment. So in this case, I'll just go to this blue icon here. If you see the blue icon here, I'll just right click this. So let me right click this. When I right click this, you'll see that it shows that there's an open terminal, open with Python, open with IPython, open with Jupyter. So I want to open the terminal. So after opening the terminal, this is what we're going to get. This is our command prompt. So let me just try to zoom it. So this is our command prompt for the system where I'm working on. So you can easily see that is showing that I'm on the base environment. So what I will do, ladies and gentlemen, remember I said if you want to run the Streamlit application, what you're gonna do, we need to write the following commands. Under this, you must write Streamlit run. Then under the Streamlit run, after that, they must put the file path. There must be a file path, and this file path should be a Python file. It should be a Python file inside the quotation. So this is what we want to show here. So it means I'm going to say here, I'm going to say stream. Okay, let me just Streamlit run. Streamlit run. Then inside the quotation mark, then I have to paste the file location. Remember the file location where we stored the Python file and the module file. So now within this, I have to write the file name of the app. Remember, if we can go back there. So this shows that I need to write this as Market Cap Prediction app. So this is what we wanted to show here. So what I will do here, I will just say / then I'll write the name of the file, Market Capitalization Prediction app, but this should be as a Python file, like what I said, as a Python file, then inside the quotation, then now we have to run this. We have to run this. And then after running this itself will automatically open the app after running this. So in other words, you can also go to command prompt. Then after running your terminal, then you type Streamlit run, then with your file path, but it should be as a Python file. Should be a Python file. The one I said we need to save it earlier. So let's just give it some time. It will just display the the result is still running. It's still running. So this is the code that we use actually to run the app on Jupyter when using Jupyter notebook from Anaconda Navigator. So this is very important. But remember, it depends with your system. If you're using Google Colab, then the system will not be the same. The system will not be the same. Or if you're using Spider, then the system will not be the same. Right. Let's just give it some time. Oh, there it is. It has now opened the link. Automatically, it will display. You see, it has now displayed the okay, let me minimize this. It has now, it will now show the Streamlit app that I have already created in order to do the model deployment. So let's just give it some time while it's still running. So you see, it shows now that it is running. So let's just give it some time in order to display the results. So you can easily see here, it says it's still running. Okay, I think it will complete soon. Let's just give it some time. So all the time, if you want to use Jupyter Notebook in order to deploy the app, it means you need to create a Python file like what I said. You create a Python file, then after creating a Python file, you download that Python file that is the app codes, like what I just said. Then after that, then you save it in one folder. Whether you can either use your local desktop, then you just save it there. Then you need to make sure that when you are when you call it as a file path, but as a Python file. So it's still running. Let's just give it some time. Okay, let's now display the app. I believe it has completed now. Yes, still running. Supposed to display the futures here and also the banner of this app and also the prediction button, but still running. Yes, now it's coming. So you see now it has displayed the app. This is the app. However, it took some time due to the connections, but it's still running, which means it has not yet completed. It must display the predict. So you can see that on the side here, it has shown the futures that we need to input here in order to make the prediction. So you can easily see that from at the bottom here, there is a predict button, which will predict the market cap based on the inputs here. So what we can do now, we can just say, okay, fine. For example, let's say we just have to say, okay, fine. Let's say we know the inputs here. Just for example, let's say we know the revenue. Let's just assume the McDonald revenue, it's around, let's say now it's 10.89. Then the earning, it's let's just say 5.28. Then okay, let's just say it's around 15.28. Price to earning, let's just say price to earning is around 2.5. It's just an example. Then price to book value, let's say price to book value, it's negative 1.98. Negative 1.98. Operating margin, let's just say operating margin is 30.79. It's just an example, percent. Shares outstanding, let's say shares outstanding, it's roughly 2.58. And cash on hand, it's only 0.33. Dividend yield, let's just say the dividend yield is 3.5%. The net asset, let's just say the net asset, the net asset in the company, it's roughly 1.66. It's just an example. Then the total debt, let's just assume the debt in the company is around 0.01. It's 0.01. So this is the input. By the way, ladies and gentlemen, if we go back to our analysis, for example, in terms of those futures that were highly correlated with the market, with the market cap. Remember, we dropped the earning per share, but when you look at the correlation between the net asset and, just an example, between the net asset and the market cap, you can see that there's a negative correlation between the net asset and the market cap. What does this mean? It means that an increase in asset will eventually result in a drop in the market cap, but an increase in operating profit will result in an increase in market cap. But however, correlation is not the same as causation. So for example, you see that there's a negative correlation between the shares outstanding and the market cap, which means if we increase the shares outstanding, the market cap will decrease. So they're inversely proportional. So these are the things that we need to take into account. Like, for example, in the context of an asset, remember I said if we decrease the asset, if we decrease the asset, it means the correlation, the market cap will will be higher. So this is one of the factors that we might try to observe from the app. So let's now go back to our app. Then in our app, remember we have inserted these values, the revenue, the earnings, the price earnings, the price to book value, the operating margins, the shares outstanding, cash on hand, dividend yield, net assets, and the total debt. So let's now come to this and make the prediction. So we want the app to make the prediction. You see, it says that the market cap in $1 billion, it's 107.86 based on this input. Like, for example, let's say we want to try to change the net asset. We want to try to change the net asset. Let's just say we reduce the net asset. Instead of being 1.66, we make it to be negative 1.66. So you see now we are decreasing the net asset. Let's predict the market capitalization. You see that by decreasing the net asset, the market capitalization has actually increased from 107 now to 109. So let's just return it back again now. So let's make the predict. Let's predict when it's now 1.66, when the asset is 1.66. You see that when the asset is 1.66, then now the market capitalization is actually becoming lower. But how about if we increase the cash on hand? Let's say we want the cash on hand to be 0.40 now. The cash on hand is 0.40. Let's just make the predict. So remember, it was 107. You see, now it's 107.86. There was just a slight increase in terms of the cents. But yes, a slight increase in terms. So it means cash on hand does not have that huge impact towards the market capitalization. But when we look on the factors like, let's just say earnings, say revenue. Let's say the revenue now it's around, let's make it 10, it was 10.89. Let's say 10.90 now. Let's just say we want to predict when the revenue is 10.90. So let's just make the predict. Remember, it was 107 point something. You see, now it's 107.86. So it has slightly increased. So this is the app that I actually created to make the predictions, and I will also share the link in order for you to have access to the codes that I've actually done. Thanks for listening, and don't forget to like, subscribe, and hit the bell button. Thank you very much. Bye-bye.